Hey gals, today we're going to talk about projection. So this is another type of transformation. So we're going to fill in one more corner of what transformation is. So for this, I've actually regressed to the 19 final model matrix, that code we had back then. So you can go ahead and do the same thing, just cleaning up a little bit so we have a cleaner project to work with. So here it is, and this is pretty cool. This is pretty next gen, I would say, but it's too bad that we're only using 2 dimensions, right? Because this is supposed to be a 3D engine, and it's called 3D programming, 3D graphics. So I mean, pretty disappointingly lack of a 3rd dimension so far. So why don't we try moving this little boy, this little guy in 3D, huh? Let's move it to the middle, and I'm gonna set its size to be 1 again. So if I just provide 1 floating point, that should initialize all the components of the vector to 1. So it's a nice shorthand there. And instead of rotating him around the z-axis, which is the axis pointing out of the screen, so instead of rotating around that axis, I'm actually gonna set him to rotate around the y-axis, so the top, like the axis pointing upwards. So he should spin around, like on like a table spinner, whatever, like a little ballerina. So I'm gonna do that. This would be like yawing, in the Euler angle sense. So there we go. It doesn't exactly look 3D. I don't know what about you guys, but I mean, it doesn't look 3D. I mean, it looks sort of like he's scaling up and down. He's flipping around, so you're seeing like the front and the back of this cool ass guy, but I was expecting something cooler. So let's actually talk about what 3D in the NDC square means. So I'm gonna pop this up because I've been lying to you guys. I've been being dishonest. It's actually not a square; it's a cube. I think I've mentioned this before. So I'm gonna draw the NDC cube here. So let's draw a couple of corners. Like so. What? And a random space. What? That's the wonky looking cube, but it's okay. I'm sure you guys will understand. The back sides there. There we go. So there's 3 axes, right? So we have the x-axis, which is along this direction here. That's the x-axis of the NDC cube. Then we have the y-axis going up like that. And then we have the z-axis going out of the screen like this, so going towards us. So this point over here, like this back point here, that is -1, -1, -1. All right, so the back left down point. And then the top right forward point, this one. I threw the arrow in the other direction, there we go. That's 1, 1, 1. All right, so it goes from -1 to +1 in all the axes. And then 0, 0, 0, the origin, is smack dab in the middle, like somewhere around here, I guess. Smack dab in the middle of the cube, that's 0, 0, 0. And so far, we have been working sort of in one slice of this cube. You can sort of see that's the square slice here, like the middle slice. Because we've been just hard setting Z to be 0. So we've been sort of working in this area. If you can see that, it's like, one plane filling in the, like one slice of the cube. And we've been working there and moving around, moving here and there on that plane, but we have never left that plane. But now, since we're rotating around, the y-axis here, our plane is actually spinning around right now. So, we might start out, I hope this sort of makes sense almost. We're sort of spinning around, we're starting like this. So here's our little square in the middle of the cube. That didn't turn out very good. Try again. Wow, that's bad. Okay, whatever. It's there. Here's the shadow, right? And then we're spinning it around. So after a while, it will sort of point maybe like this. Whoops. And here's the shadow pointing that way. So we're sort of filling up more space in this cube. its vertices are moving along the Z axis of this NDC cube. So even though it doesn't look like it, they are the vertices of this this spinning square here is actually moving through the Z axis, moving back and forth. All right, but there's no perception of depth here. There's no, like, you know, things that are getting further away or getting smaller. What happens with the NDC cube is that everything just gets squished up, right? It's just sort of you can sort of take it as like you take it like a pancake, like, press it together, and that's what gets, you know, projected to the screen. So you can almost see like the screen is like a camera here, and it just sort of captures just whatever it's looking at without any depth or anything like that. He sort of looks straight on, and that's what's end up on the that is what ends up on screen. So we ourselves have to do something to change this projection, to add some sort of another layer to transform these vertices to say, no, they're not only supposed to be like on screen like they are, we want it to be like stuff that is further into the NDC square gets smaller, and stuff that's further, you know, front, that should get bigger because it's closer to us. We want to mimic how we sort of see real life, and that's done with a transformation. That's done with a matrix. All right, so now we're gonna do that. Oh yeah, and I should talk about clipping as well. I should do that first. What happens if we go outside of this square? Okay, well, if we go off the sides, we've already kind of seen that. If we go, you know, if we go out of the, you know, X bigger than 1, you know, that's off screen, so obviously we don't see that. And same with the Y direction. If we go off the Y plane here, down here, we'll also be off screen, so obviously we won't show up anything. But what happens if we go out the Z, you know, Z of this end or Z towards the camera this way? What happens then? Well, the same thing happens, even though it's a little less obvious. If I just move this our little plane back and forth, right? So I'll move it in the Z direction with sine of time times 1.5. So I'm moving it to like 1.5 units forward and 1.5 units backwards. So we're going like back and forth on the Z plane. Let's see what happens. Okay, so you can sort of see that it's there, and then it's like, whoop, it vanishes, and then it comes back, and then it vanishes. And then it comes back, and then it vanishes. And that's it going outside of the Z plane. It gets clipped. It's called NDC clipping. And the reason you kind of see it like, you know, sort of halfway going away and then showing up, and it's like gets swept away and then shows back up again. Well, the times it's visible, it's when it's, you know, within the NDC cube. So when its Z value is less than 1 and bigger than -1. But since it's tilted, you know, since we're rotating it, one edge might go out of this cube earlier than the other edge. So that's why you see it like, you know, one edge goes out, and that's when it starts to clipping and sort of fading away, as it's one edge going up nose first, and then the rest comes after it. So that's why it doesn't go out in one big bam. It's just pixels that are outside the cube gets clipped, and the pixels that are inside the cube gets rendered. So this is not on a vertex basis. This is on a fragment basis. Every pixel does this NDC clipping test. All right, so it's not the vertex basis. It's on a pixel basis. So that's why we can see half the square being rendered. Cool. Let's make it not to go anymore. All right, whoops. All right, so we're gonna make this this perspective transformation is what it's called. So I'm gonna make a matrix for perspective. I'm actually gonna call projection. Okay, I'm gonna call this perspective function, and perspective creates a perspective matrix. All right, and that's called I'm gonna say perspective is one type of projection. We're also gonna look at another type of projection called an orthographic projection. We're gonna start with this. So perspective creates for us a projection matrix that creates this perspective illusion, where stuff that's further away, deeper into the screen with a more negative Z component, gets smaller, and then stuff that's closer up gets bigger. All right. Yes. So let's do that. So first, it wants a field of view, and that's the field of view of the cone. Let's draw this actually. Let's what the fuck am I talking about? Here's the camera. And you can see it as a cone coming off from the very point of the camera here. So here's gonna be a cone going out like this. All right. And it has some field of view here. I'm gonna call it A. And generally, how projection works is that, if we have some object here, so here's like our little guy, our little plane, his cross section of the cone here defines how big he will be on screen. So if I draw the screen here, this guy takes up roughly 50% of the screen or something, so he will end up, somewhere here, taking up 50% of the screen. But stuff that's further away, maybe over here, if we look at his cross section of the cone here, we can see that he is much smaller in relation to the cone, so he will also end up being much smaller. So he takes up maybe 1/5 or something, so he will be over here being 1/5 of the screen. And the mathematics sort of works out with like, okay, how much smaller are they getting? Well, it depends on the field of view, because if this field of view was smaller, tighter, then maybe it's like this guy will show up as so big that you can't even see, he doesn't even fill the screen completely, while this guy will still also look relatively big. So it means that stuff that's further away stays bigger on screen. So the bigger the field of view, the more stuff gets, included in the viewport, and the smaller things will seem on screen. Like stuff proportionately will shrink on the screen. And the way the mathematics which proportional to each other is that if you go one distance, one unit distance, I call it the h, it will be twice as big on screen as something if you go h further distance. So if you go another distance h, this thing will be half as big on screen as the thing before it. And this is true for any distance. Any distance h you take, if you travel another distance h, that will be half. It will half in size, assuming the things are the same size, of course, proportionally to the cone. So that's sort of how depth works. It doesn't really matter that much, but I just wanted to give you like what is depth, what is perspective, and that's mathematically it's sort of how we talk about perspective. Yes, so let's go. So field of view is the angle of this cone that defines how much stuff we see and how small that will be. And let's set it to 90 degrees or something. That's a good field of view. It expects it in radians, so I'm just going to call the radians functions to convert 90 degrees to radians. Then there's the aspect ratio. So that's another neat thing with the perspective matrix. How I've been saying, we have basically a square, but it's actually a rectangle on screen because we have a rectangular aspect ratio of the window. The perspective matrix will also take your aspect ratio of screen into account. So it will, it will grow the viewport a little bit on the x-axis because our window is a little bit bigger on the x-axis. So I'm gonna get the width and height of the window. So I'll do glfw get window size, just to feed that into our perspective matrix. So I will take width divided by height, and you have to make sure to convert one of them to a floating point, or you will get integer division, in which case decimals get thrown away, and we will get, 1 essentially, unless it's twice as big, and then we'll get 2. So remember to convert one of them to floating points, which will make it into a floating point division, and then we'll retain our decimals. It's a very easy trap to fall into. Sorry, I'm just gonna close that real quick. Right, and then we have the near and the far plane, and this is the section of the cone to take into account, because remember what I said, the NDC cube, the NDC cube has a clipping plane, the front and the back. If you go above 1, you get clipped. If you go under -1, you also get clipped. And this defines how to map this cone onto the z-axis of the NDC plane. So, if I set my near plane to be here and my far plane to be here, these 2 objects will get included, but this one will not be. So maybe this is a distance of 10 and the far plane is distance of 100, and that is away from the camera, that is. So this defines how to map these things onto the NDC cube in the end. So now, if we have a clipping plane of 10 to 100, we will actually consider objects 10 units away as minimum, and then 100 units away as maximum. So we will take those and map that into the NDC cube. So we're moving away from the NDC cube a little bit in that regard, about like how much depth we can use. One caveat is that we cannot go to 0 or below 0. And that's because, the mathematics of how to convert something from, how big is it on screen to, how big is its cross-section on the cone to how big it should be on screen. As you go closer, stuff starts being bigger, right? If you take your hand, which might be something, some size, and you start bringing it closer and closer to your face, it's gonna grow. And as it gets closer and closer, it's actually gonna explode in size, right? As you get really, really close, it grows much faster than when you're over here. Remember, because of that, each distance halves it. Each distance halves the size of my hand, which means that it goes very big, then it halves, then it halves, then it halves, then it halves, and halving something will create this curve where it sort of peters off. But the other time is where I bring it twice as close, it grows by 2 times. So I bring it close to the same amount, and it grows by 2, and I bring it up close to the same amount, and it grows by 2. So it's just gonna explode, right? So that's why there's something called a singularity. At the 0 point, like when you're actually at the camera, you have a singularity where it will, the curve will just go like zoop, and it will go up to infinity. So if you actually have 0 distance to the camera, it will essentially boil down to an x divided by 0 equation, which doesn't make any sense. It creates a singularity. So that's why it's forbidden to have a far plane that's at 0, and even more below 0, because what does that even mean? Like, does the cone like reverse or something, and it goes like negative, and it's like you see the 4th dimension or something? No, can't do that. So negative near planes are also forbidden, because it doesn't make any sort of mathematical sense. Yeah. So near plane I'm gonna set to 0.5, maybe. Like, it's okay to be a small number, like it just can't be 0. And then far, I'll set to 10. Why not? The reason why you might want to keep these numbers into sort of a normal numbers, like you don't want to put like 99999 as the far plane, because things are gonna get very crammed into the NDC cube if you do that, because it's mapping 10 to, if you do a really huge number, it's gonna map all of that into the NDC cube, which means that most of your objects are going to be crammed against the far plane here, while this is just empty space of nothing because you've set such a big far plane. And that will actually cause floating point imprecisions. So, the depth calculations will sort of mess up, because the floating points are just not precise enough to handle objects that are so close to each other in the NDC cube. So you want to try to spread them out on your NDC cube as much as possible. And that means, looping the near and far plane, sort of wrapping your scene around those two as neatly as you can. without, you know, obviously having them clip. But yeah, that's why you don't want to put like, you know, an absorbent number as a far plane. If you you know, if you can avoid it. So let's see. Okay, that looks pretty good. Nothing happened because I made a projection matrix and I didn't apply it in any way. So how do we apply it? Well, it's a transform like everything else. So it's a way to transform matrices in from this like regular NDC cube, I guess we can call it world space, transforming that into some sort of projection space. We're gonna talk more about spaces later in the next few videos. But the way you do that is to just multiply it just the same way. It's just a transformation. It's nothing really special about it. We just lop it up at the beginning here. So I'm using the projection times. And we want to do that after we've done all the modeling. So the model vertices are where they should be in world space, or, you know, whatever space we're in. I guess we're in world space. You want to do the projection absolutely last when everything is where it should be. So let's do that. And let's run it. Okay, that's not good. It's empty. What did I do wrong? Well, I didn't do anything wrong. I knew it was gonna happen. You think I make mistakes? Are you stupid? I'm the smartest human on the universe. No, of course not. You have 3 videos of me making mistakes and then being like, fuck, I made a mistake, and then you restart the video. So the way it has now is that we have sort of a camera. I'll call it a camera for now. Position at the origin. Oops. It's not actually a camera. It's not actually at the origin, but it's more easily explain what's happening here if we think about it that way. We have a camera here with a camera cone like this, something. It's 90 degrees, but it's way less, but whatever. And it's positioned at the origin, and our cube, or sorry, our square, is also exactly at the origin. So our square is just like roughly here, spinning around. So it's sort of spinning. But why aren't we seeing it? Because it should be spinning like, if we're sort of looking from the side perspective here, it should be like turning, whoop, and it should be laying on its side like this, right? Assuming this is looking, you know, in the negative z direction. Then why aren't we seeing anything? Because now it's in the cone, so we should be seeing something, right? Well, remember the far and near plane. What did I put those to? I put it to 0.5. And how big is our square? It's 0.5. So our near plane is exactly here. So, you know, we might get a pixel or something if we're lucky, maybe, but it's not gonna enemies capture the actual square by any like real sense. What happened with that sentence? What the fuck? Okay, anyway, so we have our near plane here at 0.5. So how do we do this? Well, we could move the camera, not easily though, and we're gonna be doing that soon. But one way to rev this easily is to just move the square out, right? Just place it somewhere in front of the camera so that we can actually see it, right? So it's in the cone and not like right at it. So I'm just gonna, in the translation here, I'm just gonna put, it's in a negative direction, remember? Because positive means coming towards the screen. I like poked my own face. It's coming towards the screen. So we want to go in the negative direction, going a bit away from the screen, just to sort of get in view and take a nice selfie. So I'm gonna put it 5 units maybe. That was positive. Negative 5 units maybe, like into the screen. So let's see what happens. Hey, there it is. And we can see that it's sort of, you see the edges are sort of tilting. Let's put it a little bit closer. It was a little bit far away. Let's do 2. Okay, a little closer. It's 1. It's a little shy. There we go. Okay. So now you can clearly see the perspective going on here, right? The closer edges are closer to the camera, while the further edges are the closer edges are bigger. That's what I meant to say. And the further edges are smaller. So we can clearly see like a perspective going on with our little plane here. I'll put it a little bit further away. It was a little bit extreme with the. I'll do 1.5. That's probably good. There we go. Okay. So great. So that's a projection, a perspective projection. What other type of projections are there? Well, there's something called orthographical projection, which is not really as fun as perspective, because, you know, by default we kind of have an orthographic projection where there is no depth, okay? When things get far into the distance, they always stay the same size. So an orthographic keeps proportions to what they are in the real world, or what they are in the, you know, in the whatever world we're working with. So it doesn't do this fake things get further away, they should get smaller, right? So we can just do one of those real quick. So we can do math 4. Projection is equal to ortho, and then left, right, bottom, top. And now we're actually defining. Let's actually write this out a little bit. So here we had the cone, right? Well, the ortho is just a cube. So, you know, if this is the camera here, here's the camera, here's the point. The orthographic is just defining a cube like this. And it can go on like however long it wants to. And, you know, if here's our little plane, it will just retain its proportional size to this cube. So, you know, okay, it takes up roughly 50. So on screen, this cube will be roughly 50% of the screen. And the same goes for like this plane, and it doesn't matter where they are, they always retain their proportional to the cube. And what we're doing with the sizes here, the left, right, top, bottom, is that we're defining the positions of the sides of this cube. So left means how many units to the left is the left face of the cube. So let's do minus 0. Let's do -1. So we're sort of defining our own NDC square. You can sort of see it like that instead of having, you know, -1, 1, -1, 1, -1, 1, instead of having those like defined sides, we can define those sides to be whatever we want. So we can do like, you know, let's do -0.5, for example. So the left side is going to be -0.5. The right side, we don't even have to do +0.5. We can call that, I don't know, 1.5. So we're like shifting the NDC cube to the right or something. And then bottom, and then top. So we'll do bottom is let's do -1, 1. And then the same thing with the near and far planes. Those are defining the front and back of the NDC cube. But unlike with projection, where I said like, projection, unlike with perspective, where I said you cannot be 0 and you cannot be below 0, that is not the same with orthographic, because since this is a cube, we can just easily extend this cube backwards, and, you know, it retains its shape. So this camera can actually capture behind itself, right? So that's why the analogy of a camera sort of breaks down a little bit. But we don't have that restriction for the orthographic. When I have 0, we can have -0 or negative whatever we want. It doesn't really matter. I'll just do 0 and we'll look 10 units in front of us. Yeah, sure, why not? So let's see what happens here. Okay, so that's kind of what we expect, right? So I made the left side of the orthographic cube to be -0.5, which means that, you know, this the side, or like from this middle to the side of this square is 0.5 units. So it's actually touching like the orthographic wall here, and then there's this huge empty space over here, and we can see it like it is -1.5 units away, but we can still see it because we made the orthographic depth be, you know, a lot of units. Whereas if we differ this from if we didn't have projection at all, yes, we don't see anything, because since we're translating our little square to be -1.5 units away, it's outside of the NDC cube, which means it gets clipped. Every single pixel gets clipped. While if we make an orthographic projection matrix, then we can decide to be like, oh, we can see stuff 10 units away. We don't care. We map those anyways. So if you don't want perspective, then you want to use an orthographic matrix or orthographic projection. And the other nice thing about having an orthographic projection matrix is that we can also define our window's aspect ratio. So if I just save aspect here, we can just multiply the sides by the aspect ratio. Let's do this. I hope I took the right aspects now. I don't remember. Yeah, that's right. Yeah, okay. So now the square is actually square, right? It doesn't matter how I resize this now. The square will always pertain to its square aspect ratio because I built the aspect ratio into the orthographic matrix. So it defines the NDC cube, or the orthographics cube, to have those proportions. Because this is because I made the sides be 2 in width and in height. If you sort of think about like what's the distance between the left and the right wall, it's 2, and what's the difference between the bottom and the top face, it's 2. So if I times 2 by the aspect ratio, it should work out, but I have to make sure that I start with the same number. I can of course make it as off aspect if I want to, if I just put in random numbers. But anyways, so that's another type of projection, and this is very useful for top-down games, or for that matter 2D games. If you're making a 2D game, you probably don't want depth, you probably want everything to stay the same size, so then an orthographic projection is very good. Also, if you're doing a top-down game, sometimes you want perspective, maybe a little bit perspective, but other times you want to keep everything the same size, so you have a very nice overhead view of things. So then that would be a very nice use of the orthographic projection. Of course, that being said, the majority of every single engine has perspective projection, because that works in 99% of games, and that's usually what you want when you think 3D, but orthographics also there, so I wanted to mention that. Alright, so that's projection. And I've been talking a little bit about cameras. I've been thinking about projection like a camera. Next time we're actually going to talk about the camera. We're going to talk about how do we move this view around uniformly so that we can actually move around our scene and see stuff from whatever angle. So that's what I'll be talking about next time. So see you then.